Welcome everybody to another Cross USA lecture. This is our second virtual, remote, live streamed Cross USA lecture of 2022. Our Cross USA lecturer this year is Silas Nichols of FHWA, and you will be hearing more from him in just a moment. In the meantime, I, of course, am Brad Keeler. I'm the director of the Geo-Institute. And if you do not know anything about the Geo-Institute, you should head on over to geo-institute.org when this lecture is over. And there you will find out that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and/or geologists. And we are part of the American Society of Civil Engineers. If you like what you see today, and I guarantee that you will, you should do a few things. Maybe you should click like under this video. You should also click subscribe. You should click get notifications, and we will let you know every time we post something to the YouTube channel. One more plug before we get started. If you have not joined the 96 Club already to support Geo-Institute student programs, you could go do that after you are done watching the lecture today. You can get information about that at geo-institute.org, and a contribution of $96 gets you a Carl Terzaghi bobblehead for a limited time while we still have them. If you think that is something you would like, and I think you would, you should head on over there and do that as well. And now, the main event. Here to tell you a little bit more about the Cross USA lecture is our local involvement committee chair, freshly returned to Atlanta from the chapter summit, which was a big success this weekend in Virginia. It is Jeremy Varner from the Federal Energy Regulatory Commission, aka FERC. Jeremy, take it away.
Hey everyone, and welcome to this lecture. I'm Jeremy Varner, and as the LIC, the Local Involvement Committee, the LIC, as the LIC chair, one of my roles is sitting on the selection committee for the Cross USA lecture. What the Cross USA lecture is a program of the Geo-Institute where we select every year one leading technical expert who's also a great communicator to travel around to the chapters and graduate student organizations of GI and present a lecture. We look for lectures, with a lot of technical, good depth and breadth of experience, but also from across the practice. So we've had professors, practitioners, but we had been missing anyone from the government sector. Even though we've been doing the program since 2010, we hadn't had any government sector engineers, and so we were trying to get somebody from the government, and that's when we thought of Silas. He's like, anyone who's been around GI's probably interacted with Silas at some point, and we're excited to hear from him today. Silas Nichols is the Principal Geotechnical Engineer for the Federal Highway Administration's Office of Infrastructure. He has his BS in Civil Engineering from Syracuse University and MS in Geotechnical Engineering from Tufts University. Mr. Nichols provides leadership and direction for the FHWA National Geotechnical Team through policy support, technical developments, and coordination with industry and professional groups like the GI, which is why he's always very active in GI events. Silas's experiences in both public and private sector engineering work. Professional experience includes design and construction services for numerous routine and complex or unusual projects throughout the United States, development and delivery of instructor-led and web-based training for continued education of transportation engineers, development and delivery of university courses, invited and keynote presentations, authoring technical articles and editorial columns, and various levels of participation on technical and steering committees. So now, without ado, we turn it over to Silas Nichols. Take it away.
Thanks. I appreciate it. I think all of the promotion for this was titling this presentation Challenges with Large Diameter Foundation Elements, but I think it's more appropriately titled Addressing Issues with Large Diameter Foundation Elements, as you're going to see here as we go through this that FHWA and a lot of our partners in the industry are doing a lot of work to address some issues that we see as prevalent in the geotechnical discipline, and I think we're really moving pretty quickly to address some of these issues that we think have caused a real problem in both the design and construction industry. Before I get started, it is federal government, so I'm required to put up a disclaimer. I will let you read that. I will not read it for you. I'll just babble a little bit here and say thank you again to the Geo-Institute for this honor. This has been so much fun this year, and I still have a lot to do with this Cross USA lecture series. And I'm really looking forward to some of the upcoming in-person visits around the country. This has been really a great opportunity. And I think the most important thing that I've been able to do with this is to really highlight some of the work that FHWA is doing or funding, and to help people understand what it is that we see as a program as outstanding issues in the discipline that we think are overarching and need to be addressed, and to lay out essentially what is our strategic plan as we move forward here in the next few years. And so if I were going to start anywhere, I guess I would start with just what the FHWA geotechnical program looks like. And we are a really, really small group set up to handle supportive policy and guidance here in my offices and headquarters. We have a research team out in Turner Fairbank in Northern Virginia. We have a technology deployment and training group that is a virtual group located in our resource centers around the country. That's all on the federal aid side. We also have a federal land side that is, for all intents and purposes, a Department of Transportation for federally owned roads. But I'm really going to be focused today on the federal aid side, the program side. And here, what we do, for all intents and purposes, is update, maintain, design and construction documents for geotechnical features. We provide tools and resources for more efficient delivery of programs at the state departments of transportation. And we look for ways to identify and implement innovations and new technologies as they come along for what we believe are more cost-effective highway construction solutions. And at the moment, the technical focus areas that we are really dealing with are outlined here. There are 5 that we are pouring funding in primarily: innovations in geotechnical design and construction methods, advanced site characterization, geotechnical asset and performance management, and then the sort of they're all multidisciplinary, but the ones that are not necessarily associated as primarily geotechnical items, scour and pavement, areas where, because we are a Department of Transportation with bridges and roads, we feel it's really important for us to be involved in those areas. But the one we're going to focus on today is the first one, the innovations in geotechnical design and construction methods. And our program objectives are pretty simple. We are trying to really address what is a rapidly evolving geotechnical construction industry, and we're trying to do that through research and document or guidance development. We're looking to address innovations in structure foundations, earth retention, and ground improvement that are really in the last 2 to 3 decades have been extraordinary and difficult for us to continue to write governance around. And so some of the areas that we are working in actively are in large diameter foundation elements, which is what I'm going to be talking about today. Some of our barriers to increased use of shallow foundations in transportation applications, some of our contracting and procurement issues as we continue to get more innovative contracting structures in place to deal with our more complex program and project delivery issues. Some issues with acceptance criteria and equitability and acceptance for geotechnical construction. And then finally, some of our ground modification issues and governance around what we're going to do with some of those. And so really what I'm going to talk about today, or what I'm focused on today, is just the first item, the large diameter foundation element issues. And I guess we could go back to the beginning and just talk about what it is we do with a deep foundation element with respect to design. I mean, traditionally, we've always thought about a nominal resistance or an ultimate resistance, however you want to determine it, as some combination of a side resistance and an end bearing. And that's pretty standard. I think the thing that is not explicitly written on this slide, but everybody is aware of, is that you must move a foundation in order to mobilize any of that resistance. And this really gets us to the root of the problem. As the elements get bigger in diameter and deeper, you have to move them much further in order to mobilize something that we would term a nominal resistance. And at some point that becomes impractical with respect to how we apply design. And this really is something that just comes out of the beginnings of the practice, right? We've developed all of our design methodologies based on our analysis of load test databases, all kinds of different models, including finite element and finite difference models, our own experiences regionally around the country and around the world. But the issues that we're starting to see are pretty extraordinary. And so the big picture issues for deep foundation elements are rooted in this idea that in probably the last 2 decades, the evolution in just how we construct foundations has been significant. And I'll get to why that might be the case here in just a second. But it's allowing us to have much greater load carrying capacity, much larger magnitudes of load. The demand per element is greatly increasing. Our materials and the demand on them is increasing. And as a result, whichever one, the chicken or the egg, the nominal dimensions of these elements are getting really, really big to accommodate really complex loading conditions. And so if you think about what has happened, and I'll speak specifically to transportation, over the last few years, and really during our transition from working stress design to a limit states platform load and resistance factor design, some of the things that we're designing for now, we really didn't pay much attention to in the past. So loading conditions like scour or vessel collision, seismic issues, kinematic loading conditions like lateral spread. All of these are issues that we really didn't design for in the past, but are now part of this more complex loading condition issue that we have to deal with. And so enter the emergence of large diameter foundation elements. And this, like I said, occurred really in just a little over 2 decades, that we went from an average, we'll take a drilled shaft as an example, but an average drilled shaft being no more than about 4 feet in diameter and no deeper than 100 feet, to things that we're seeing today. There's an active project going on right now in the country with 12-foot diameter shafts proposed that are going to go down in excess of 220 feet. That is a different foundation design problem than the one that we were used to seeing just 30 years ago. And it's not very different on the driven pile side. We were very used to very small diameter elements that we were driving into the ground, but now we're looking routinely at 6, 7, 8-foot diameter driven piles that we have to figure out how to not only control them during construction, but determine what the load carrying capacity is going to be on them when we're done. And, the evolution here is partly due to, advances in installation equipment. On the drilled shaft side, the development and the implementation of rotators and oscillators. On the driven pile side, just bigger and bigger and more capable hammers have allowed us the ability to build bigger elements. But really, this advance is mostly due to our advances in load testing, our ability to put bigger and bigger loads on things. And this has allowed for the industry to have much greater confidence in the design and construction of these elements, and hence our comfort with making them bigger and bigger and bigger. And so to address some of this work, the Federal Highway and others have already really begun to do a lot of work in addressing some of this rapid evolution. And I'm going to talk about a lot of this during this presentation today, but documents that we have finished in the last few years include our drilled shaft manual, GEC 10, our driven piles manual update, GEC 12. We recently developed a document on lateral loading on deep foundations, GEC 9. We've completed research developments on large diameter open-ended piles. So that's open-ended piles of diameters of 36 inches or greater. We've done some work on post-grouting of drilled shafts, and that has led into some other work The SHARP 2 program, the Strategic Highway Research Program, in its second incarnation, R19B project, was focused on calibration at the service limit state for load and resistance factor design. We're looking at construction means and methods for large diameter foundation elements. And so NCHRP Panel 2451 is now in its beginning stages, is active and is working toward addressing that issue. The optimization of load transfer and drilled shafts. So this was follow-on work to the FHWA post-grouted work that was done for Caltrans. Control of materials such as trimming concretes and high-strength steels. The Federal Highway Administration has done recently some work on trimming concrete. We are actively getting ready to start more research on trimming concrete. And then finally, the acceptance requirements and procedures for large diameter foundation elements, or just foundation elements in general. We recently published GEC 15. It hasn't been formally announced yet, but it is available for download on the FHWA website. But it is a document that looks at procedural information on how to properly go through everything you have to make an acceptance decision on a deep foundation element. And so that's the stuff that is either active or recently completed. And what I wanted to do was talk about drilled shafts, then driven piles as the two primary foundation elements that we're dealing with in-house. I could talk about micropiles, I could talk about aggregate piles and some others, but these are the two real predominant elements for which the large diameters and the depths of them are getting to the point that we've had to start looking at some really significant changes and some real research to address. And so I'm going to start with drilled shafts. And I'll start with the fact that back in 2018, we published an update to our drilled shaft manual, GEC 10. I recognize that it has not been easy to get your hands on because it hasn't been available for download. We're working on that now. I have every expectation that we are really close within a few weeks of having that online and available for download. But the drill shaft manual was updated in 2018. It was a really short turnaround from the previous version of it because the evolution in this area has happened extremely rapidly and we haven't been able to capture everything we needed to capture. As a result, we had to really start a major update to this document five years after the previous version of it. And so the things that we were able to address here included the shafts becoming much larger. I'd already mentioned that, back in our 1999 version of this manual, it was designed with the idea that the shafts were never going to be larger in diameter than about 4 feet, and they weren't going to be deeper than about 100 feet. That's just not the case anymore. They're much deeper. We have new means and methods for installation, significantly longer concrete pours, which is its own headache, much larger load carrying capacities. And then we've got this idea of what to do with these load transfer curves. When you are picking up side resistance versus when you are picking up end resistance, and can we do something to optimize that in order to make the design process and the sort of performance of a drilled shaft more efficient? And so along the way, within GEC 10, we were able to address some really low-hanging fruit. And one of those was the use of prototype shafts. Everybody is familiar with demonstration shafts or load test shafts that are done on projects, and for transportation, we're no different. We, in our previous manual, allowed for the use of prototype shafts on any load shaft project, with stipulations that are pretty common in the literature. At least half the diameter of a production shaft on the project, a minimum of 30 inches if nothing else, constructed using similar tools and construction techniques, and then some information on what to do about exposure time and unit values for side and base resistance with respect to the diameter of the shaft that you're actually looking at. And so the real big issue here was that as the elements got bigger and bigger and bigger, it was no longer a sure thing that you were going to be using similar tools and construction techniques on your prototype shaft as you would be doing on your production shaft, which makes the element different. And we thought we needed to address that relatively quickly. And the way that we went about addressing that here recently was to differentiate construction phase load tests from design phase load tests. And so the idea here is that in design phase, the main purpose of load tests is really to establish what unit side-based resistances are going to be available in the regional geology that you're working in. And so we've left the information on design phase load tests alone. We still allow prototype tests under the previous information. Construction phase tests, we think, are a different animal because we need to be able to replicate construction means and methods and the time for the concrete pour. And if you're interpreting the words correctly, what I'm basically saying is that the uncertainty in a larger diameter element is really on the ability to repeatedly construct that element over and over again, and not necessarily on how much load nominally the element can carry. And this is important. And so for construction phase tests, we now have written in that any load test done in construction phase after letting, that shaft needs to be the same size as the largest production shaft on the project. And really, this is, like I said, to assure that a contractor can repeatedly construct a shaft and deliver the project in accordance with the requirements to justify whatever higher resistance factor we're going to allow them to use as part of design. The second piece of low-hanging fruit was about the interpretation of bidirectional load tests. So as the elements got bigger, the idea of top-down static load tests became impractical. The development was the O-cell, but there are now a bunch of different versions of bidirectional load cells out there for bidirectional testing. And what you're looking at here on the left, figure A, is just a typical bidirectional test result coming back in. Figure B on the right is the top-down construction from the bidirectional test. And what we were really interested in here is making sure that the report backs from load tests were accurately conveying what actually happened in the load test and what is available for load carrying capacity in the element. And so the interpretation of a bidirectional load test is pretty standard. If you're looking at points 4 on the figure on the left, figure A, really what that is the load corresponding to a deformation of 0.4 inches. We can take those 2 points, add them together, go over to figure B, and you get the constructed point in the top-down curve. And that's fine. That's what we expect to see. The problem comes when you get to side resistance, which is the top curve in figure A, when you get out past 0.5, when the shaft has failed. And in order to construct the remainder of that side resistance curve, you would have to extrapolate it out, which is what they've done here in figure A. And then correspondingly, you get an extrapolated curve in figure B. And our issue is that this is not a measured load. This is not a correct interpretation of the bidirectional load test. And we have written into the new GEC 10 better language to help people understand how to not only interpret a bidirectional load test, but to how to appropriately apply it to the situation that you're using in order to justify the use of an increased resistance factor. Some of the additional issues that we've been looking at, full depth steel, the previous versions of our document really only suggested that steel be extended to a minimum of 10 feet below where the plane, below where fixity is essentially provided in the shaft. This is a subjective determination. It also, because you don't have steel going all the way to the bottom, doesn't allow for acceptance testing in ways that are common for drilled shaft elements. And so we've adjusted the language there to require a minimum amount of steel for the full length of the shaft. We also felt like this was just a basic ease of construction issue versus having to just hang a cage that's only partially the length of the shaft. Regarding concrete pours, as they got longer and longer and longer and bigger and bigger and bigger, we were doing a lot of these large diameter shafts, these deeper shafts in urban areas. And the issue just became, could you get concrete to the site in a manner that allowed you to continuously make the pour? And so we're still working on this item, but for current purposes, we've rewritten this section to essentially ask for a minimum amount of concrete to be on site prior to beginning a pour so that we have a better likelihood of actually getting to the end of a pour continuously. So along the way, we recognize that we still had some gaps. And so we have been conducting some research here in-house. One of the pieces of research that was completed a while back was on trimming concrete. The research was conducted by the University of Missouri, and we were looking to address issues specific to what we called mass pours and geotechnical applications. We went through a significant literature review, and we essentially placed a significant focus on understanding factors contributing to what we thought were factors contributing to the performance of concrete, including primarily thermal issues and bleed and segregation issues. And the effort itself focused on some numerical modeling and some laboratory scale testing to look at this. And we did not ever actually publish the report. That doesn't mean that we didn't learn anything from it. It just means that we don't believe that we've asked the right questions right just yet in research. And so we're doing some more work on this, and I'll talk about this toward the end of this presentation. But we are in a large effort to try and address some of our issues with trimmy concrete or large pours under trimmy conditions. The other piece of recent research that we've completed was on post-grouting of drilled shafts. We published a report back in 2017 that looked at this. This was completed principally by the International Association of Foundation Drilling, ADSC. They had a number of subs that I will not take the time to name here, but they were the lead on this. And what we were asking for here were some recommendations on how to bound the use of post-grouting for our current state of knowledge, how to quantify improvement mechanisms for post-grouting. We wanted to look at the development of design methodologies for its appropriate use and look for some methods for verification. And this research came about, I think we initiated it at the end of 2012, and it came about because we were starting to see more and more value engineered projects around the country that were looking at the use of post-grouting, and not necessarily for remediation of shafts, but to more efficiently design the shaft. And we were being asked a lot about, what to do about this. How can we bid it? How can we design it? Can we really use this? And so we asked the research team to start investigating what's really going on when we post-grout a shaft. And so for those of you unfamiliar with post-grouting, pretty simple procedure. From an ungrouted shaft, we can install or just have through the existing tubes that are in the shaft for non-destructive testing. We can blow out the bottoms of those and or set up a different system. We can grout at the tip of a shaft. By grouting at the tip of the shaft, we can mobilize that tip, which then results in a negative side resistance, or the shaft starts to move up in the ground, a positive tip resistance as we engage end bearing. And we can measure various criteria, pressure, displacement, volume, strain, until we meet a criteria that says that we have effectively improved the tip resistance in a drilled shaft. Once you're done post-grouting, you have for all intents and purposes, preloaded or pre-mobilized the tip of the shaft. And then once you go back into standard axial loading, you're getting some result that features positive side and positive tip resistance. But I think the most important thing that happens here is that you have engaged tip resistance much faster by just stiffening the response at the tip. That allows us to move the load transfer curve a little bit, and you now start to pick up tip resistance at the same time that you're picking up side resistance. This is extremely important. And so the research looked at 3 different devices, and this research was, like I said, done by ADSC, the University of Missouri. Eric Lohr and Andy Beckman were really the principals here doing the majority of the research work, but they looked at 3 different devices for for loading the tip of a shaft. And so the one on the upper left is the standard sleeve port. It's an open system. The middle one is the flat jack, an enclosed system that allows us to better control the volume of the grout. And then the one on the right is not a post-grouted system, but it is a rim cell. It is a hydraulic system for proof loading shafts. So those were the three systems that were sort of looked at. And the significant findings here, well, maybe I should say the significant finding here is that we were able to identify a predominant mechanism for improved performance at the tip, and that was pre-mobilization of the tip of the drilled shaft. Now, some other things happen, as would be expected, especially with the sleeve port system. You can get some ground improvement as the grout sort of escapes into the soil matrix, which would contribute to an improved performance in the shaft. You can even get some run up along the sides of the shaft. Generally, this is associated with a loss of control of grouting. In both of those cases, could you use them? Yeah, but they're really, really difficult to bound the limits of and to figure out what you're really getting from it. Much more complex effort. And so really the big issue here was this idea of mobilizing the tip of the shaft. And so what do we get? Well, now you're looking at a standard series load transfer curves for a drilled shaft, just generically. And so displacement on the horizontal axis, resistance on the vertical axis. You can see that we have blue lines that would be for an unconventional or conventional ungrouted shaft. The dashed red line is for a subsequently post-grouted shaft. And the thing to pay attention to here is what happens with the base resistance. And so at the same deformation, the base resistance as a result of post-grouting is actually improved, which allows us to get a combined resistance that's improved at that deformation. Now, it should be pointed out that ultimately you don't get any change in you don't change the capacity of the shaft, the combined the ultimate resistance of the shaft. They will eventually converge where they're supposed to converge. But all we're really doing is changing the way or the rate at which tip resistance is acquired by just stiffening the response at the toe and moving that load transfer curve over a little bit, which is a big deal if we're thinking about how efficiently we can design shafts in the future. And so we're headed down a number of pathways with this. The acceptance issue is probably the biggest one. We need some metrics for verifying that improvements are occurring, and we need them to be rational. So it should make sense to you that if you've got an ungrouted shaft in the ground, you've had to go through a lot of work to actually accept that shaft. Going in and grouting the tip of it is, under every circumstance, improving the shaft. How do you verify that without making it an undue burden on the contractor or the state for assuring that that improvement occurred? And then methods for measurement of that. We were looking at a design methodology and the implementation of that, and that led to some add-on work for the California Department of Transportation, Caltrans, that was done by the University of Missouri, again, led by Andy Beckman, who was a PhD student there at the time. And so the work for Caltrans, and we paid very close attention to this, really looked at two fundamental considerations for implementation of a design procedure that considered post-grouting. And it was establishing a level of uncertainty that was specific to the loading device that you were using to create this bidirectional load at the tip of the shaft. That would be the way that you could appropriately select a resistance factor that essentially looked at the way you were mobilizing the tip and what the uncertainties were in that methodology. And then the second consideration that had to be addressed was establishing an appropriate magnitude for what that bidirectional force needed to be, right? So you need to proof load it enough, but what should that target be and how do we determine what it is? And so that research, I'm going to throw some stuff up here that really is in its infancy. You should not take any of this as anything that the Federal Highway Administration is publishing. But what you're looking at here is probabilistically calibrated resistance factors on the y-axis against a normalized bidirectional force on the x-axis. And they're plotted for 4 different levels of uncertainty in what would be the mobilized proof load. And those 4 different levels of uncertainty are shown as the coefficients of variation in the legend. And so a CSV of 0.0 would essentially be a perfect load. And so it should make sense that less uncertainty, higher resistance factor. But at some point, and in this case, it's showing as below about 0.3, there really is no benefit to this idea. There's no reliability benefit to proof loading, right? The load itself is independent of both the magnitude and the uncertainty associated with the mobilized device. And so there is some baseline associated with how you would look at this data. And so from here, the research team was able to start to look at ways of proposing levels of uncertainty for different ways of mobilizing this tip resistance or applying a bidirectional force at the base of a shaft. And so it doesn't really look at anything that is considered a traditional bidirectional load test device, mostly because we weren't looking at them. But it should make sense as you're looking at a chart like this that a sleeve port, which is an open system and a little bit less controlled than everything else that we looked at, would have a higher level of uncertainty than, say, a flat jack, for which the grout is contained within a space before it actually starts to apply pressure to the tip. And then a rim cell, which is a hydraulic device, which would be even more reliable or less uncertain. And if you were going to add bidirectional devices into this, they would be at least as good as a rim cell or better. I don't know if I should be using a word like good, but that's fine. Anyway, and so this would be an example of something that is, and this was subjectively sort of established based on some measurements during the research. It is absolutely on the conservative side, but it is an idea of where we might be headed as we think about the future of drilled shaft design and construction. And so if we were really sort of thinking this out, and again, this is the last slide I will show that comes out of this piece of research, where we might be headed is something that looks like this, where again, we're looking at resistance factor against normalized bidirectional force. And now we've actually sort of taken the methods for how we're going to apply the bidirectional force and now have them with the chart. And so it should make sense that we would have some lower bound that is based essentially on what we currently do in past practice. And then once you've gotten to how you're going to actually apply the bidirectional force, you can start to apply an uncertainty to that method that allows you to look at an increased resistance factor associated with your ability to, for lack of a better term, proof load the shaft by stiffening the resistance at the toe. Now, you're probably looking at this and you're thinking to yourself, well, does this mean that the Federal Highway Administration is telling us that we're moving toward this idea of testing every shaft? I don't know if that's true yet, but for large diameter shafts, it would make sense. And quite honestly, the idea of more testing is not foreign. We do this with other deep foundation elements. But I think it provides us a much more rational approach and probably a more cost-effective approach to design and construction of drilled shaft foundations, especially large diameter ones, and a much higher level of comfort with their long-term performance and reliability. And so that's essentially where we are sort of heading with the research in drilled shafts. Now, we are not close. We are still a ways away from getting to something that I would think is implementable. But as you can see, we're moving pretty quickly to try and address some of these issues. And I think we're getting close. We're on the right track here, and we are getting close. And so what about driven piles? That would be the other sort of problem that we have right now as the elements get bigger and bigger and bigger and bigger. And so back in 2016, we published our update to the driven piles manual. And driven piles have been a staple. It is our most popular foundation element. It's been pretty easy to do these updates to just handle the advances in technology that have come along. But we did still have a gap with driven piles when we got out of this document, and that we didn't really have a way to address large diameter open-ended pipe piles, both concrete and steel. That was where the big evolution was coming in. We're now also seeing really large H-pile sections, which are also a different problem. But But we needed to start to look for a way to address these larger diameter elements, how they behaved, what kinds of things we could do with them in the future with respect to design, construction, and acceptance. And so we needed to go in and to look at some differences under both dynamic and static loading conditions. We wanted to collect and analyze some available data, whatever available data we could get our hands on load tests, and then evaluate the applicability of our current resistance factors and design methodologies to these large diameter elements. And so back in 2020, we published a research report that is downloadable. This was led by the principals were Catherine Pedic and Bob Mitchell from Shannon and Wilson, with Mike McVeigh from the University of Florida, and then a host of others. But we asked them to take a look at those questions. And the way they approached this was to essentially establish what we knew we didn't know, what our known uncertainties were in the system. And so, it started with just the basics. This actually comes from a training course that we developed probably 20 years ago that at the time, was conscious of the fact that we had a number of different ways for doing a static analysis design for a driven pile. And based on that, we've got a bunch of these methods out there, and we had to sort of figure out which ones worked best for us. And of course, we settled on a couple, and they've been our basics for pretty much as long as we can remember. And so we went forward with the known uncertainties of having a number of different existing static design methods. We had the known uncertainty of plugged and unplugged conditions. For small diameter elements, a little bit easier to deal with. We are pretty confident with small diameter elements that we can achieve a plugged condition in most soil conditions. And under those circumstances, we would get something that drives down with a base resistance that is tied to a plug acting as sort of a closed-in element. But as the pile gets bigger and bigger and bigger and bigger, it starts to cut through the soil, and it is unclear whether or not it is plugging or when it plugs. And if it isn't plugging, the base resistance looks a lot different during driving. And so construction control is a problem. Once it stops and it sets up, what are we really getting? If we have to restrike a large diameter pile, can we actually get enough? Can we get enough out of the hammer to mobilize it to tell us what it is we're seeing? So these are all known things that are uncertain about driven piles that we sort of felt like we had to deal with research. Load testing, just static load testing. Static load testing is really, really expensive, and it's really hard to get a bidirectional device to the bottom of a driven element. And so, it's not routine for us to do a lot of large diameter static load tests, especially to failure. And so just the known uncertainty of having enough data. And then dynamic load testing. And this one, I think everybody's aware of. We are now a much more reliant discipline on dynamic load testing for driven piles, but the interpretation of large diameter open-ended elements is much more difficult than smaller elements. Again, this mobilization of resistance, especially during restrike, and then what the plug behavior is and how that plug behavior is being represented during construction control. And so these were the sort of known uncertainties that we were trying to address. And so Shannon and Wilson and University of Florida went back. They dug up one of our old FHWA load test databases. We asked them to reconfigure it. They did. They put a better face on it. And then reconstructed all of the data. They then added a whole bunch of data on large diameter open-ended pipe piles, 113 steel, 42 concrete. That database is available. You can actually go in and download the database. If you just Googled FHWA and load test, deep foundation load test database, it will take you right to it at our Turner Fairbank Research Center. It is a static database at the moment. You can't add or modify the database, but you can access the more than 1,500 piles that are in there. And so from here, I think that the most notable thing that jumps off the screen at you is that for the large diameter open-ended piles, not as much data as I think we thought we were going to come up with, especially on the concrete cylinders. Just not a lot of data. And so when we got into the research, several meetings got us into a position where the selection considerations for how we would analyze the database focused only on steel piles, only open-ended piles, only those that were loaded in static compression. They had to have instrumentation, only impact driving methods, and you had to have available subsurface information. And so that seems pretty simple, but quite honestly, that was not as easy as you might think. We have a lot of incomplete load test data out there that is difficult to use. And so we ended up with what is a considerably smaller data set than I think I anticipated anyway. We grouped the load test data sets by site condition, cohesive, cohesionless, and mixed. In order to get to some uniform section, you had to have 70% or greater of either cohesive or cohesionless material along the pile length. It turned out that with the three groupings, we really didn't statistically have enough data. Shannon and Wilson and the University of Florida went in, played around a little bit, and were able to create two more intermediate groups based on differences in the materials, both in bearing and inside resistance, that give us a total of 5 data sets. And from there, here were the sort of parametrics that they looked at. And so they went in, they dug out 48 different static design methods to look at. That seemed like a lot to me. I don't think it was everything. They looked at ASHTO methods, DOT methods, offshore methods. They had some methods in there that were specifically developed for CPT data or to account for pile plugging. They looked at plug development, which turned out to be much more difficult to evaluate than even we were expecting, despite the fact that we knew it was going to be difficult to evaluate. And then the one that off the page to me, we looked at load test failure criteria, and they looked at 12 different methods. 12 different methods. If I gave you a load deformation curve, I could put 12 different methods on it to, depending on what was going on, to try and determine what failure would be defined as that for that pile, which is its own problem. We're going to be addressing that here in some current research that we have just let just 2 weeks ago. So we went into resistance factor calibration. Here were the sort of parametrics for that calibration exercise, the 5 data groups. They ended up taking the 12 failure criteria. They got that down to 3 that they thought that were the most reliable. 12 different design methodologies, 4 in base, 4 inside, 4 that were combined, 2 target reliability indices, 3 resistance factor methods, and then 2 data versions. And when everything was said and done, the draft report that was produced for federal highways listed more than 6,000 resistance factors for these combinations. And so, you know, at one point they had sent over a series of tables that looked like this, where you might have the method for the failure criterion, the different methods that they looked at along the x-axis, the considerations down the y here, and then this combinations of tables. And so these went on for days and days and days and days, and we sort of got to the end of the exercise, and the recommendations that came back from Shannon and Wilson included some revisions to existing static design methods, as well as a couple of additional ones, some explicit recommendations for what to do about plugged and unplugged conditions, some specific resistance factors that are being recommended to federal highways, and then a recommendation for what the load test failure criteria should be. And, you know, there again, we're not really close to, I think, solving the bigger picture problems that were really brought out by this research. There were some things that are inherent, they're relics of the geotechnical design discipline that just simply are being blown up by the fact that the elements are getting bigger and bigger and deeper and deeper. But we did go in and try to make some recommendations to ASHTO, the design specifications. This has not been actually done yet, but we're looking at how this might be applied in current design practice. And so what you're looking at is the resistance factor table that is in the current version of ASHTO. The highlighted areas are areas that would be changed as a result of the large diameter open-ended piles being incorporated into the specification in a different way. This is not final. Do not take this as something final. But we recognize that we'd have to make some adjustments to what to do with wave equation analysis and whether or not it's applicable to large diameter piles. We'd have to take a look at the use of driving formulas like engineering news and whether or not it is applicable for large diameter piles. And then there are some recommendations for the static analysis methods that you would use or would be preferred for use for large diameter piles in clay and sand and in mixed soils. So that's where we are right now, and that is the sort of logical evolution of the research that we published just a couple of years ago. Like I said, there's still more work to do. And where we are headed with this is that we've got to start looking at the acceptance procedures and the determination of a failure criterion. It is unacceptable, I think, that we have all of these different methods for determining what we think failure is in a large diameter element. And it makes the idea of calibration for resistance factors something that is not a rational process. And we've got to do something about that in limit states design. There's also a need for additional data, a lot of data. It is our biggest problem, is our lack of data. We need more data on concrete piles. We need data on piles with constrictor plates. We weren't even able to look at those. And then the dynamic testing method work is its own problem. And we've got to find a way to not only get more data there, but figure out a way to get to a consistent interpretation of what the dynamic testing data is telling us. So that would be the issues for the driven piles. And so I'm going to put one more slide up here, and this will be the last slide of the presentation. And really, this is focused on our outstanding issues for just large diameter elements in general and where we're headed. And so the big one right now is this reevaluation of geotechnical limit states. So FHWA just the week before last led a contract, or I guess it was about a month ago we led it. We just kicked it off the week before last. This one will be led by Dan Brown and Associates with the University of Missouri as the principal investigator. There are a cast of thousands working on this from all over the country and around the world. And so we're going to be looking at really the applicability of LRFD to structural foundations, and this is specific to bridges, structural foundations, and whether or not we need to do some different things with regard to the definition of specifically the strength limit state, but the geotechnical limit states in general. We are also letting a second effort here. It should probably be announced as let in the next 2 weeks on trimmy concretes. I think we asked the wrong questions the last time around. And so this time around, we have redefined the parameters of the research to help us better understand what we think are measurable metrics or what needs to be measured within a trimmy concrete during construction and during control of construction that would allow us to more accurately understand what its long-term performance is going to be. And so both of those projects are 30-month to 3-year projects, and we hope that as we get closer to the end of those, we'll be able to better see what the future of geotechnical design is going to look like in that area for structural foundations. NCHRP has just opened up a project 2451. I think I mentioned it earlier on the effects of construction methods on unit resistance. We really, since the evolution of the construction industry to rotators and oscillators, we really haven't taken a close look at what the impacts of construction methods are on unit side resistance and board piles. And so NCHRP is asking that question. And then the assessment of current construction control and foundation acceptance procedures. GEC 15 is now on the street. That's good. And it covers such things as the use of performance testing and the frequency of testing and other metrics that are correlated to performance, specifically inspection. And so we still have, I think, a lot of work to do there also. Our technology is far outpacing our ability to understand how the technology works with inspection and other tools that we have available to us and not instead of. And so as we move forward, the challenges are big, but I think we are in a really, really fun and just amazing space with respect to where the future research is going to go and how agencies like the Federal Highway Administration are going to try and address them. And so with that, I will say thank you. And I will turn it back over.
Thank you very much, Silas. That was really enjoyable. Even as somebody who doesn't practice in deep foundations, there's a lot to think about. And we have several questions coming in off the YouTube. If you have questions, just type them into the chat and we'll get to them as they come in. Starting off with large diameters like 12 feet and depth of 100 feet, the concrete can behave like a mass concrete. Do we have to consider the recommendations of the ACI 207 to remedy thermal effects on concrete?
So this has been an important question. It's probably been the most common question that we're seeing in this arena is should the mass concrete issues as defined by the structural community also apply to such things as drilled shafts underground? And it is one of the questions that we are currently asking as part of the research. I don't have the answer to that. And without better information, the answer has traditionally been, yes, we should look at certain types of pours as mass concrete and treat them as mass concrete. I am of the opinion that the issues associated with pouring a concrete by pump or by TRIMI underground under the pressure of a slurry, and then either within temporary casing or against soil, have the mechanics of it are very different than just pouring it on the surface and putting a vibrator to it. And I think we need to think about geotechnical concrete in a very different way. I don't know what that way looks like yet, hence the research. But absent any other information, a lot of our state departments of transportation are still treating it as mass concrete. There are even some flaws in that logic because we look at definitions of mass concrete by diameter of shaft and not really by volume of shaft, which is its own problem. But it is an important question that we are trying to get our arms around right now.
All right. How do we correct a faulty pile in a group of pile foundations?
Well, I don't think my presentation covered that, but there are a number of ways to do that. The one thing I wouldn't do is just take a backhoe, as we see all the time, and just push the pile back. And I think we have to look for some other things. But we have a bunch of different ways addressed in our driven piles manual for handling piles that are out of tolerance. I don't know that I want to eat up too much of our question time on that. It wasn't really part of the presentation.
All right. Will these developments be incorporated into the respective NHI courses?
Eventually, yes. I should caveat that by saying that the way that our NHI courses have traditionally looked is going to be changing here shortly. We are going to be, just due to some advances over at NHI, we're going to be able to go back and add content on a more in-time basis. So we'll have accessibility to new content as part of the National Highway Institute in different forms. So you won't just have to get it from a course.
Okay. When doing integrity tests for piles and finding some concrete integrity issues at the base of the pile, what do you suggest as a solution to fix the problem?
I mean, there are a number of different solutions, but I think it's the answer is more subjective than it is not, in that not all anomalies are created equal, not all base issues are created equally. And so you certainly do not want anomalies, and you certainly do not want issues at the base of your shaft. But there are some boundary condition issues that show up as false positives when doing certain types of tests. There are ways of actually either post-grouting, which was essentially a remediation technique before we ever thought about it as a optimization technique for design of drilled shafts. And then in some cases, it may not be necessary if, for instance, you are relying only on side resistance, or if it's just deemed by any combination of engineers and analysis that the anomaly or the issues at the base are not significant to your long-term performance of the shaft. So I think that's a more complex question than just what do you do?
Okay. Does the database include any energy piles?
No. Federal Highways has lightly looked at energy piles, but we really haven't found a practical use for them just yet that is more efficient than our current means for dealing with roads.
Okay. Has the diameter any effect on the hysteretic behavior of the pile when analyzing it under lateral cyclic loading?
So I'm sure it probably does. I don't have a good answer for this. So yeah, I just don't.
Okay, hey, that's fine, man. And then what types of industries, projects, or loading conditions usually involve designing LDOEP?
So what has been happening a lot for us is that in certain types of construction applications, we're running into these issues where our footprints are getting smaller, but we have unusually large loads that we have to deal with. It turns out that we can get really, really high capacity out of large diameter elements. And by using a few large diameter elements, we can actually get into smaller footprints. So it works out to be somewhat efficient for us to use large diameter open-ended piles or large diameter drilled shafts in certain applications.
Okay. And then knowing that dynamic testing typically underpredicts capacity of large diameter open-ended piles, can static or statdynamic load testing be used to calibrate the results of dynamic testing?
So that's kind of where we're headed. And by where we're headed, I mean, I for the short term, I would generally be recommending to people who are doing this that if you do not have good knowledge of a good experience with your geology and the type of foundation element that you're putting in the ground, that you should be load testing elements in an effort to better calibrate the results of dynamic testing. We do have some state departments of transportation that actually, once you get over a certain size of pile, actually require a static load test, at least approved test to calibrate dynamic testing. So.
All right, I have a more general question, or philosophical question for thinking about your presentation. With these new, it's about innovation, and innovations in these foundation systems, and I get, I guess the thought is, it's easy to dream up a new fancy bridge. But I guess an interesting thought is government's role in innovation. A lot of times we don't think of government as as pushing innovation, but without FHWA's work on new construction methods, safe policies for building the foundations. How does without the government taking that role, how do we innovate as an industry? I guess I don't have a really clear answer. Just that was a thought. A lot of times you don't think of government as innovating, but clearly without FHWA or other government agencies taking a role in the innovation, it's not going to happen, or it's not going to happen safely. And I don't know if you could talk about that for a second.
Yeah, so this is an interesting question. And is it a chicken or egg question? I'm not 100% sure. I would argue that Federal Highways right now is reacting to private sector innovation more than we are innovating for the private sector. That as the construction industry continues to find efficiencies in the market that allow them to do different and better things, governments are forced to do research on how they work and why they work and how we can both design and bid them and then put together requirements that allow us to accept them. And so I think it's a back and forth, but I think right now we're more reacting to innovation than we are driving innovation. Although I think in some cases, some of our reactions drive more innovation.
Okay. And then, are there FHWA-led efforts to aid industry into conducting full-scale testing to aid in building potential calibration data?
So I'm going to carefully answer this question. The Federal Highway Administration really isn't in the business of funding individual load tests around the country. Or around the world. There are just too many variables with geology and methods of construction for it to be useful as something that we would expend a lot of money on. Load tests are expensive. I do think that the transition to load and resistance factor design and some of our current work is asking others to do more load testing as part of calibrating practice to their local conditions and as part of fulfilling this idea of building more data. So I think that's the correct answer to that.
All right. I think we have maybe just one more. When I have tested drill piers of 1 meter diameter in soft rock for lateral loads and deflection with depth, the load deflection curves typically show deflection with no load initially. How do I fix it?
So that's a technical assistance question, and maybe we could you could just, if that's a transportation related question, you could probably just send that to one of our resource center people to help you out with. I don't know that we want to spend a lot of time here with that. So.
All right, and finally, another less technical question. Obviously, all the work you do with foundations with FHWA is to support, structures designed by structural engineers. Your work is highly multidisciplinary. I guess, do you have any lessons learned about working with multidisciplinary teams? Any thoughts on working with structural engineers?
Yeah, I mean, I think every day I am reminded that while what geotechnical engineers do is exceptionally important, we don't actually own any of this stuff. And, we support bridges, and the bridge is the asset. If you wanted to get away from foundations, we build foundations for pavements, but the pavement is the asset. And I think I think if we just sat down structural engineers or pavement engineers as the two primaries in my agency, they would tell us that we were too self-important. And I try to explain to them that we're not important enough to them. So I think that's really where we're headed. It is a broad, angry debate all of the time about whether or not bridges float or, roads are built on nothing. So.
Well, those are good closing thoughts. Silas, once again, thank you very much. Thank you very much for being the Cross USA lecturer. I know you're still visiting a few chapters and graduate student organizations left this year. And based on what we've seen today, I know everyone's really going to enjoy your visit. So thank you very much. And I'll turn it back to Brad.
Thank you, Jeremy, and thank you, Silas. And I will make one pitch to all of our viewers today. You have before you two public sector employees who are both geotechnical engineers. If you have ever thought to yourself, and you should, I would really like to explore a career in public service, you can contact us and we will put you in touch with either one of these guys and they can tell you all about it and help feed your thirst for service. We would love to have you in the U.S. government making a difference with your knowledge and expertise. So thanks again, Silas. Thanks to all our viewers for your questions today. You had some great ones and we had a bunch. That's great interactivity. We're really happy about that. We will have one more. Maybe Silas's jaw will drop at this one. Cross USA lecture virtually later on, probably when it starts getting a little cooler outside. So something to look forward to for that. Other things that are coming up soon, we'll have GeoStrata Extra next month in August. We will be doing something. We will decide what that is at a later date that will be very soon for Harry Seed's 100th birthday in August. And in October, as always, we will have Terzaghi Day. So you will have a remainder of the summer and a great fall with lots of great stuff from GI. Again, like this video, subscribe, get notifications. We'll give you a lot more good stuff, we promise. So thanks everybody for tuning in today, and we will see you all very soon.